Hi class, today we are talking about the properties of limits. So we're just going to kind of refresh the concept of what a limit is, learn how to refer to limits at infinity, and then look at some different properties so that we know what we are quote unquote allowed to do with limits and what we're not allowed to do with limits. So I've broken this lesson into two videos. The first will be just going through the properties, and the second will be the examples. So let's recall that the statement, the limit as x approaches a of f at x equals L, says that the values of f at x get closer and closer to L as x gets closer and closer to a from either side, such that x does not actually equal to a. So we're getting closer and closer to a, but not actually getting there. Therefore, there is no need to consider x equals a. The only thing that matters is the behavior of f at x near x equals a. Okay, so now let's look at limits at infinity. So I said previously that a limit must actually be a real number in order to exist. So a function must be approaching a specific number in order for that limit to exist. However, often functions approach infinity. So even though the limit technically doesn't exist in this case, we still use the notation once in a while, just again for ease of understanding or showing what we're trying to say. So let's just create a function here. So a rational function. So it's approaching this here, and then we'll make like a quadratic-y looking thing here, and then another one of these guys here. Okay, and then let's say that, let's label where these asymptotes are. So let's say that this horizontal asymptote is at y equals 1, because you can see that this rational function has the same degree on the top and the bottom. So it will be the ratio of the leading coefficients, which we can see is 1. So that would be our horizontal asymptote. And we can also see we have a vertical asymptote at 3 and a another vertical asymptote at -1. So we can say here that the limit as x approaches 3 from the right, so from the positive side of f at x, what would that be? So as we get closer and closer to 3 from the right, what is the function approaching? It's approaching negative infinity. Okay, so this means that the limit does not exist since it's not a real number. However, sorry, I was just supposed to end the paragraph there. Okay, but let's take a look at what about the limit as x approaches infinity. This we are allowed to talk about. The limit as x approaches infinity. So x can approach infinity of f at x. So as x approaches infinity, the function is approaching 1. You can see that it's approaching the horizontal asymptote. So this limit does exist. So I just wanted you to get the difference in the understanding that if there's an infinity here, then the limit does not exist. Okay, the limit can't equal infinity for it to exist, but you can have x approaching infinity as long as then the function is approaching a specific real number. Okay, so now we're going to move on to properties of limits. So we learned that if a function is continuous, we can plug and chug, which basically just means that we can substitute in the x value for the variable and assume that f at a is the same as the limit as x approaches a of f at x at that point. However, if we have a problem like this, okay, so the x approaches 5, the limit does not exist. So that is because we know that this is a rational function and x equals 5 would indicate a vertical asymptote, as can be seen by the denominator, would be 0 if we substituted 5. So in that case, the limit does not exist because the function will be approaching infinity or negative infinity plus or minus infinity on either side of a vertical asymptote. So that's how you know it doesn't exist there. But if the result is 0 over 0, this is the indeterminate case. So we call this the indeterminate case, and we have some work to do to solve the limit. So think graphically, this point is a hole. So there might still be a limit. So even if the function doesn't exist there, there may be a limit. It may be approaching something specific. So that's what we're going to be dealing with a bunch of our examples. So now let's look at some of our properties. So the limit as x approaches a of k is just k for any constant k. Well, think about this. If k is a constant, we're talking about a function like y equals, let's say, 4. Okay, so think about it. That's just a horizontal line at y equals 4. So no matter what x value you have, that limit will still be 4, because no matter what you're approaching, no matter what x value you're approaching, your y value is always 4. So we could say like the limit as x approaches, I don't know, 10 of 4 is still 4. When x is approaching 10 from either side, y is approaching 4. Okay, so what about the limit of x? Okay, so think about it. This is talking about the function just y equals x, just the line. So as x approaches a of x, the limit will be a. Okay, so think about it. So the limit as x approaches 5, so when x approaches 5 on either side of the line y equals x, y will be getting closer and closer to 5 as well, since it's just the equation y equals x. Okay, so this next statement is saying if we have the limit of a function plus another function, you can separate out the limits like this. So the limit of the first function and then the limit of the second function. So for example, if we have the limit as x approaches 2 of x squared minus 3x, let's just say plus 3x, I can separate that out into the limit as x approaches 2 of x squared plus the limit as x approaches 2 of 3x. Okay, that's all that means. All right, now this one says that if we have a constant being multiplied by a function, I can actually take that constant out to the outside of the function. So let's say I have the limit as x approaches 2 of 3x squared plus 15. Well, I can simplify this to the limit as x approaches 2 of 3 bracket x squared plus 5. So I can separate that out into 3 times the limit of x approaches 2 of x squared plus 5. Okay, so I can take this 3 because it was common factored out and actually put it outside of the limit. All right, now this one just says, again, if I'm multiplying two functions together, I can actually multiply the limits of those functions together. So if I have the limit as x approaches 1 of x squared times x plus 2, I can turn that into the limit as x approaches 1 of x squared, and then do that all times the limit as x approaches 1 of x plus 2. Okay, similarly, we have division here. So if you're dividing two functions, you can just divide the two limits, provided, of course, the limit as x approaches a of g at x is not 0. Okay, so if we have a rational function, like the limit as x approaches 3 of 2x over x plus 1, I can divide that into the limit as x approaches 3 of 2x divided by the limit as x approaches 3 of x plus 1. Okay, and finally, if I have the limit of a function that's all raised to a power, I can take the limit of that function and then raise it to that same power. So for instance, if I have the limit as x approaches 3 of x to the power 5, I can evaluate that as the limit as x approaches 3 of just x, take that result, and then raise it to the power of 5. Okay, so that might all seem like obvious stuff to you, but there's a few things that I want you to take away from this. First of all, it's important to be able to read mathematical notation and to be able to understand what it means. So in your textbook, really all you'll see is the left side, all these properties, and they don't normally give you examples. And as you pursue math education past high school, they will just be giving you the notation without the examples. So it's an important part of your math education to understand symbols and properties when they're laid out in this way. Second of all, it's important to understand that just because we can do something with addition or with algebra, that doesn't mean that you can do it with everything you learn in math. So just because we can add two things together in different ways doesn't mean that you can automatically do it with limits. So it's important to not have that assumption and to make sure you do learn the properties of the different things you learn, like limits. Okay, so now we're going to be taking these properties and then using a bunch of different strategies to actually find limits. So we'll be using direct substitution, which is plug and chug, factoring, rationalizing one-sided limits, and then changing a variable in the example. So I will do that on the next video. Thanks for watching. Hope you learned lots. I almost forgot to say it.